Alright, hey everyone. So this video is meant to cover Chapter 5, the gases that are found in our chemistry final. I will not be solving any basic questions. I'm going to be leaving them for their own video as they are quite long. But if you do want to follow along with the basic questions, you can find them under here, where I marked it on this page. So, the first of the gas laws is Boyle's law, and it's essentially the relation P1V1 is equal to P2V2. The second law is Charles's law, again very straightforward. V1 over T1 is equal to V2 over T2, and the exact same relation, but we have pressure instead of volume that is directly proportional to T. I have included basic question 1 and basic question 2, the questions with the answers, in case you guys would like to solve them. They are basically just direct applications. There's nothing special to keep in mind. The only thing you should know is the units of each of them. You should know that the unit of P is, 1 minute please. Yeah, you should know that the unit of P is atmospheres. You should know that the unit of V is centimeters cubed or liters. And of course you should know that the unit of T is Kelvin, which is the absolute temperature found in all of these laws. Moving on, our third law is Avogadros' law. I'm going to start with the relation first, which is that pressure is directly proportional to the number of moles. And the same exact relation exists for volume. Volume V1 over N1 is V2 over N2. And once again, basic questions 3 and 9 are dedicated to both of these relations. They're just direct applications. You can solve and maybe pause the video and check your answer. One thing I do want to talk about is the statement of Avogadros' law, because unlike the other two laws, in which the law is the statement of the equation, Avogadros' law is a slightly different statement. The statement of Avogadros' law is that at the same conditions, i.e. temperature and pressure, the number of particles in two containers of the same volume is the same. What this means is, assuming you had two containers, container 1, container 2, just these boxes over here, and that the volume for both of them was the same. You can see that I drew them as a roughly equal size, and that they were at the same conditions. For example, STP, which stands for 0 degrees Celsius and 1 atmosphere. What this law means is that since the temperature and pressure are the same, and the volume is the same, the number of particles is the same. And keep in mind, this law makes no mention of what the gas is. What this means is I could have hydrogen here and oxygen here. I could have nitrogen over here and carbon dioxide. It does not matter. The gas does not matter. As long as the conditions are the same and the volumes are the same, the number of particles over here is exactly the same as the number of particles over here, every time, no matter what. And this is important because in basic question 3, they compare oxygen with hydrogen as a trick, and you should know that the gas does not matter in this particular law. The next equation is the one which links all of these together. It's the ideal gas law, PV is equal to nRT. You know the units for all of these. R is the universal gas constant, which is 0.082. And another way to rewrite this law is P1V1 over T1 is P2V2 over T2. Another way that this law has been written is PM is equal to dRT. It's essentially the same as this one, except that D over here stands for density, and M over here stands for molar mass. And the formula that you use entirely just depends on what has been given to you. If you're given volume and moles, you use the original one. If you're given molar mass and density, you just stick with this one. I have not displayed any basic questions for this law, but these 4 are the basic questions that deal with almost all the scenarios, so you could look at them if you want. And the last few equations you should know for all the gas laws are these ones over here, the basic ones. The ones that tell you that the number of moles is mass over molar mass, that the number of moles is molecules over Avogadros number, and also that the number of atoms is the number of molecules times atomicity. And of course, you should always keep in mind the density is mass over volume. And one last thing I would like to make a note of is that the ideal gas law refers, to ideal gases. And I will make a separate video to discuss the exact definition of an ideal gas, but the best way to think of an ideal gas is the conditions at which gases exist. So when you look at these conditions, it makes more sense. For example, a smaller gas like hydrogen, it moves around faster than a really, really heavy gas like iodine. It's easier for it to move around. At a higher temperature, a gas will stay a gas. It won't condense. It won't become liquid. At a lower pressure, again, the molecules will be very far apart. They won't be bumping into each other. They won't condense or become liquid. So these conditions over here are good for ideal behavior. It's not the entire law, but it is important to know when ideal behavior occurs. And the last thing, which you should remember for all of these laws if you plan on solving any equations with them, is the SI units, which are extremely, extremely important. Pressure should always be measured in atmospheres. You may be given pressure in millimeters of mercury or in torr. These are the same, and to convert, you should divide by 760. You may be given volume in, you should use volume in liters or in decimeters cubed. It may be given to you as milliliters or centimeters cubed, in which case you divide by 1000 to convert. And temperature should always be in Kelvin, the absolute temperature. You may be given in the temperature in Celsius, and you should add 273 to convert. And a last thing is that volume is not as strict as the others. You're allowed to keep the volume in centimeters cubed if it helps. For example, if we go back to question 2 over here, I did keep my volume in centimeters cubed, 400 and 400, and I could have converted at the end, but I chose not to. It all just depends on what unit they want your final answer to be in. Finally, the last law relating to gases is the idea of mole fraction and partial pressure. There isn't an exact statement for this, but you should know the definition of mole fraction, which is the number of moles of a certain gas. In my example, I chose to use hydrogen gas, over the total number of moles in any container or sample. Because this is moles over moles, you should remember that mole fraction has no unit, unlike anything else in this chapter. And that if you do have to calculate the mole fraction in a written exam, for example, your final answer should be without a unit. You can also use the pressure of a gas over the total pressure. This is also accurate. It will give you the correct answer. And from this, we can derive this law over here, which is that partial pressure is equal to the mole fraction times the total pressure. A good application for this is basic question 17. It ties both of these concepts together pretty well. I have the full solution here, and the boxes are the answers. Keep in mind, again, you can always just pause and see how I solved it if you would like to. Finally, I've included a summary of all these formulas. You can screenshot it, take a picture, pause the video, whatever works for you. And these should be all the formulas that you will need in the exam. All you need to remember is to always use the correct units. Always convert your answer to the unit they want at the end. You might have to convert and then convert back. And always use the formulas depending on what's been given to you. Make sure you're not just using formulas because they're the ones stuck in your head. So I really hope this video helped. If there's anything you guys would like us to go over in more depth, you can always just ask the people in charge of this channel. We'll always be happy to, and thank you for watching.